Okay, so today, 8 o'clock and 9 o'clock, we do the forward solution and then the inverse solution at 9 o'clock for both EEG and MEG. So last time we were talking about what was the current source density evidence that we should be modeling current flow that's visible at a distance in the cortex as a current dipole. So that means, like, current sort of going perpendicular to the cortical surface, either sort of up or down. And so that was invasive data, like when we do go down with a microelectrode through the layers, and we show that when you go through the layers, you see big differences in sources and sinks, but if you go sideways, parallel to the cortex, until you get into another area, you generally don't see, nearly as large differences. And so that's why we sort of summarize each little patch of cortex as basically just having a current dipole that's either up or down. And so what we want to do today is, given that assumption, let's calculate a forward solution that goes through the brain out to an electrode on the skin, or generates a magnetic field that we can record outside of the head. And so we'll start off with the Maxwell equations in the static case. And so the static case is, calculate E as if no B. So no coupling between the electric and the magnetic fields. And then calculate B from the currents. Calculate B from J. So the J vector is pretty much proportional in a simple case. It's proportional to the E vector. So the electric field, like something that's caused by a charge, will basically determine which way the current is going to flow. The current is going to flow. It's going to be proportional to it, depending on how resistive or conductive the medium is. So if we simplify down the Maxwell equations, normally there's 4 of them, but if we simplify them down for this sort of electrostatics, magnetostatics case, we get, we'll just put them up. They're not going to be that useful to us. But we'll just put them up so we could at least talk about sort of no magnetic monopoles. So the first one is that our data here. So here's our data that that electric this electric potential. So that's our data. Is equal to the divergence. So that's the divergence of the gradient of the potential is equal to the divergence of the currents. And so what are those? So this guy is div. How radiating are the local current fields at each point. These are the sources. So that's what we're eventually wanting to solve for. And this is our data. This is the actual sort of potential data, the voltages that we record. And that guy's the conductivity, because it depends, how much current you're going to get through something depends on, how conductive it is. That's just grad. That's the gradient, meaning just steepest uphill direction. And this is the div again. So our forward solution is going to be, if we have some sources, what data, what potentials are we going to get on the scalp? And our inverse solution is, given those potentials, how do we sort of calculate where the where the sources probably might be. So remember that this whole thing just ends up as a number, right? Once we take the, and same on this side. So that's just a number equals a number. So that thing turns this vector field of all these different currents into a single number. So that's one of the Maxwell equations. We sort of rearranged it and combined it a little bit. Here's another one. This one, I didn't talk about this one before, but this is one of the Maxwell equations that says the divergence of the B field is 0. And so the divergence of the E field is basically will tell you where charges are. So if you say, like, let's look at the E field, and are the vectors kind of coming out, coming out from a point or sort of going into a point, that will tell us where the charges are basically. But this Maxwell equation, again, like I always say, like when I first looked at this, I said, like, well, what good does that do me? What good does 0 do me? It's just like, what does that mean? Let me make this a little tighter. Okay. So what good is 0? So what this one says is there's no divergence of the B field. And so that means that the B field, so that means that the magnetic field is a particular kind of arrangement of vectors in space that can't possibly have any radiatingness at any point. It's always got to be sort of circulating. So you can't just, any old set of vectors can't be a magnetic field. It's very constrained. It can only have this kind of sort of circulating structure to it. So at no point can the magnetic field vectors look something like this. So that's an impossible magnetic field, because that set of vectors has divergence, has positive divergence. So that's that also, another way of stating this is that there are no magnetic charges or magnetic monopoles. Like an electric charge, you can have an electric charge. It's like a positive electric charge, and that causes divergence of the E field around it. But in the magnetic case, there's no magnetic charges that would cause any divergence. So that's just magnetic field. And then our last one, was originally called Ampere's law, and this one is how you relate the magnetic field and the currents. So that's kind of like calculating B from J. So this one is, we take the curl of the magnetic field, and it's kind of sort of backwards, because normally you think of the electric current flowing, and then you get a magnetic field that is the curl of the electric current vector, the J vector. But here we're doing it the other way around. We're saying, let's take the curl of the magnetic field. That works too. So if you sort of imagine you've got a magnetic field, and then take the curl of that, you'll get back to the current direction. And so in this equation, we've got something that constant is, how does the magnetic field percolate through a substance? Because we've got a substance like a brain, and different substances will allow less or more magnetic field to get into them compared to a vacuum. So that's a constant. That one's called the permeability. Permeability to magnetic fields. And now we have our currents here. So those are our sources again. And then that's the conductivity. And then we have the gradient of the potential again. So this thing the gradient of the potential will be, you know, minus E. This guy's, you know, conductivity, and this guy is the sources. Okay, and so that's basically how we will calculate. That's the curl of the B field. So we look at the magnetic field, and we say. So when you look at these equations, they're kind of useless in this form, you know, because they're really constraints. They're differential equations, derivative containing equations, but then we have to solve them somehow, and come up with something that we can actually sort of do a useful calculation with. So that's simplified Maxwell equations for the electrostatics case. So let's just forget about that for a while, and let's talk just more simply about a current dipole. And we're going to talk about it from the point of view of just a static charge dipole. Now, when you first hear that, it's just like, well, where's the current? You know, but remember the current, if you can sort of calculate what the E field is from the situation, you know, how the static charges are set up, that's going to tell you which way the current is going to flow. And so that's our starting point. We're just going to write out equations for the potential basically due to static charges, and then since we can calculate the E field from that distribution, then we basically know where the current is flowing, and so that will sort of give us our definition of a current dipole. So current moving in some direction from a source to a sink. So the simplest, absolutely simplest case is just one charge, just like the empty universe, one charge. So that case is, I'm really having trouble. Let's try that one more tighter. Yeah, I'll put this behind. Okay, I got it that time. Okay, so let's just start off with the potential for just a single, basically just a single charge. And so what does that equal to? So it equals a, you know, the size of that charge for something like an electron, or proton will just be a fixed thing, divided by some constants. And then divided by the distance to the charge. So this would be sort of what's the potential at a point from a charge somewhere else? And so we could write this out sort of a little verbosely as, you know, if r is the vector from our charge to our measuring point, so that's like and then that thing is just what is the length of that vector. So you can see this is fundamentally something you can do in 3D. So if we just find the length of the vector from wherever the charge is to the measuring point, that's the equation. And so that's like a really simple equation. It's just like 1 over x basically. And so what does that look like? Well, it looks like, you know, a sharp spike like this goes up to infinity, because when you get right on top of the charge, if the charge is infinitely small and the distance is infinitely small away from it, you sort of get infinity. But it's basically just 1 over x. So that is, and you know, what is that? That's the potential that you expect, you know, going in this direction as a function of, you know, how far away from the charge are you. So that's not inverse square, that's just inverse, just 1 over x. And so what is, if we sort of operate our simple, you know, Maxwell equations on this, what does this look like? So if we have a charge, say we'll just stick a positive charge there. And then we just plot that equation. If we plot, contour lines of that equation, they're going to be very close to each other here because it's a big spike, right, sticking out. But then as you go further away, the contour lines will get further and further apart from each other. And so what are we plotting there? This is the potential, contour lines. And what does contour line just means? Where the potential is constant. Yeah. So that's lines of constant potential, and it's in 3D. So it's actually a three-dimensional cloud with a sharp point right in the middle of it. But here I've sort of just drawn it in 2D, like it's just a big mountain, but it's like the whole thing is happening in 3D. And then so that's the contour. But then what is the E field? So remember the E field. The E field is just equal to the negative of the gradient of that potential field. And so that means the steepest uphill direction. So the gradient means like go to the potential field and then just find out which direction is the steepest uphill. And obviously the steepest uphill is going to be pointing toward the charge, but then we take the negative of it, and so then we get the steepest, the negative of this, the opposite of the steepest uphill is going to be pointing out. And that's going to represent the force that E will represent the force that a test charge would experience, a positive test charge. So if you stick a positive test charge, it's going to be pushed away. So basically, the E field is going to be really big near the charge, and then as you go sort of further out, it gets smaller and smaller. So that's this guy is the E field right there. And that's going to be perpendicular to the contour lines. So the contour lines are sort of where the potential is not changing at all, and perpendicular to them at every point, the E field will be perpendicular to those contour lines. So that's the simple situation for just one charge. But what we really want is a current dipole, but really just a charged dipole. So we have to write out the same equation for a charged dipole. So just annotate this. So this is, distance from measure from, let's say, from charge to measuring point. So now we just do the same thing for two charges. So two opposite charges. So I will give, so that's the simple one. So that's not inverse square, that's just inverse. But if we look at two charges and just do the same thing, what we get is something that at a distance boils down to inverse square. So let's just assume both charges are the same strength but opposite sign. So here's that same constant. So this is just the strength. And that was the conductivity there, again, of whatever like brain-like substance were inside. So in the case of two charges, the equation is basically just 1 over the distance away from the positive charge minus 1 over the distance away from the other charge. So this is like, charge 1 and charge 2. So now that one's a more complicated one. So let's just try to draw that one out. So now what we've got is a positive charge. So we got a positive charge here. and negative charge here. So if we just run this simple equation here, what we see, if we just look at the contour lines, so like right here, this would be 0 potential between them, because they're the same distance from both. And then we would have that same, same contour lines here, but now it's getting a little more complicated in the middle here. So the contour lines are kind of running out like this. So let's do a good dipole field. Something like that. Okay, so now we have to figure out where the electric field in this case is. And so the electric field, when we take the negative of the gradient of the potential field, what do we get? We get something that's sort of going around like this. And the direction is that way. So these are what the electric field looks like. Negative of the gradient, so the negative of the steepest uphill direction. And if you sort of look, you can see they're going to sort of like come out like that. They'll always be perpendicular to the okay, and they would just be going straight down here, falling off, getting smaller. So now you can see you've got this complicated, more complicated structure, and then they'll sort of come off directions like that. So how can we summarize that? So that's kind of a more complicated thing. So one way to summarize it, so especially in this part, if you're like anywhere near this kind of middle of the dipoles, it's going to be a mess. But if we make the assumption that we are at least 3 or 4 times the distance between the positive and the negative charge. So let me draw one more vector in here. So this vector, that green vector is our D vector, and that's the vector that goes from the negative to the positive charge. So if we're 3 to 4 times that distance between those two, and what does that mean in the cortex? It means like the cortex is a couple millimeters thick, so all we got to do is be like about half a centimeter away from the cortex, from wherever we're recording, and then this approximation will hold. And so then if we draw another vector to our measuring point, so here's our measuring point. So our measuring point, 3 to 4 times the length of D. So D was the distance between the positive and the negative charge. Then, so let's aim down here. So this is our R vector. So as long as we're about that far away, then we can simplify this guy down to inverse square. So that's where inverse square comes from. So this is approximately equal to inverse square. And that's basically our forward solution. So let me move that down a little bit so I can write on top of it. Okay. So this is going to be approximately equal to that 1 over 4 pi times the conductivity. And then the strength of the charges, now we'll just assume they're both the same but opposite sign. And then here's that D vector. And so what is that? That thing actually represents the, this is actually the J vector. Okay, so that's our current dipole. So that thing tells us, how strong, how strong is the tendency of current to flow in that direction. And then dot producted with the R vector. So what does that mean? That that dot product is, means we take, the length of D times the length of R times the cosine of the angle between them. So that's the dot product. And so you can see what does that mean? Well, it just means like, what's the angle between your recording position and your vector. In this case, it's going to be negative dot product because those vectors are pointing in almost opposite directions. So that's assigned, that will give you a signed number there. And then the whole thing is divided by the length of the dipole to the recording site cubed. So basically that's our inverse square. So if you look at this, you can see you've got sort of R up here, or like you've got the length of R in the numerator, and you've got the length of R cubed in the denominator, and so you get rid of one of them, and so this is inverse square, and this is fundamentally sort of what causes the major shape of the forward solution. It's basically an inverse square type phenomenon. Now, we've made the assumption that the brain is infinitely large, right? We're just, the whole universe is filled up with the brain. We've got a dipole somewhere in the brain, nothing else going on. And then we've got a recording point somewhere else in this universe-sized brain. Now, that's not true. We know that the brain isn't infinite sized, and we'll talk about, like, you've got to make corrections for the fact that the brain has a finite size. But one last time. But when you actually look at sort of like the major effect on the forward solution, it's mainly this inverse square thing. So this basically is, is inverse square. And it comes from the fact that you've got these two charges kind of canceling each other out. Because if you just had one charge, it's just inverse, just 1 over R. Okay, so that guy is basically our electrical forward solution before we compensate for infinite sized brain. So it's pretty simple. It's basically, it just has to do with where you're recording in there, and it falls off as an inverse square. It has to do, the conductivity of the medium is in there, and so that allows us to predict, for a given sized current dipole, as just defined by these charges, what the potential we're going to record at a point here. So just to sort of, drive home the point, why don't we just draw a cell in here? Like the cell should be right on top of the dipole, but I'll draw it off to the side a little bit. So if we've got a cell in here, so here's like a pyramidal cell in here. So what is this what is this trying to model? It's trying to model a source and a sink. And where's the sink? So the sink is here. That's where the current is disappearing into the, so this guy is the sink because the current is disappearing there, and this guy is the source. It's a positive charge, but that means that there's going to be current sort of erupting out of that point and then disappearing into this point. And here's what it's actually modeling. It's the extracellular currents, right? So it's easy to get confused about the sign. So it's the extracellular currents that are disappearing from this point, and then they're coming out of this point. So they're coming out of that point, and they're sort of disappearing into this point. Like I said, that should be sort of right on top of the dipole, but I just moved it off to the side a little bit. So what you're modeling, what you're modeling is the forward solution has to do with the extracellular currents, not the current. So the actual current in the cell is flowing up. Actual current in the cell is flowing up, but when we think of the extracellular currents, they're flowing from the source, which is at the top of the cell, down to the bottom of the cell, the sink. So it's an extracellular sink. So that's basically our just physical model of like how currents are flowing in the cortex based on the current source density, invasive data that suggests that this is actually what goes on in the cortex in general. Now, of course, sometimes currents flow sideways in the cortex too, and we're not modeling that. We're just modeling it as if it was kind of a radial current flow in the cortex. So basically, this guy is the EEG forward solution. Infinite brain. But it explains most of the sort of structure of the forward solution. And this is a difficult pill to swallow because what it means is it's going to be very hard to see deep sources. Because as you go deeper in the brain, you fall off as kind of an inverse square. So like even if you go like 2 centimeters down into the brain, away from your recording site, your signal is going to be very small. If you're 3 or 4 centimeters away, it's going to be almost, just immediately fall into the noise. And so that's one of the biggest factors when we get to trying to understand the inverse solution that we have to deal with. The fact that it's very hard to see deeper sources because of this fundamental inverse square law structure of the forward solution. Okay, so that's the EEG forward solution, but just using the simple Maxwell equations, we can calculate the MEG forward solution. And the MEG forward solution is different than the EEG because, so we'll call it sort of B2, because the B field is a vector. So this is the potential. So this guy is the, potential recorded, at a point, But that's just a scalar. But the B field is actually a 3-dimensional vector pointing in a particular direction. It's got a length and a magnitude. And so this one is going to be approximately equal to a very similar forward solution. So it's got the permeability in it. So that's how it's just a constant for a simple case of how much the magnetic field sort of permeates into a particular substance as compared to just a vacuum. And so that one's in the numerator, not the denominator, but it's similar to this conductivity constant here. And then the equation otherwise looks virtually identical. So it's this amount of current here. So remember, this thing represents this current direction and magnitude. And the only difference is it's cross-producted with our vector, our recording site vector, vector from the, from where the dipole is to the measuring point. And then it's again divided by the cube of the distance to the recording site. And so this one is also inverse square. So this is inverse square again. This one is sometimes called the Biot-Savart law. But you can see it's virtually identical to the EEG forward solution. This cross product, you could sort of decant that into the length of the dipole vector times the length of the vector that from the dipole to the measuring point vector times the sine of the angle between them. So it's just basically sort of sine and cosine. So that's the MEG forward solution. In the infinite case, which of course we have to correct. That's the MEG. Forward solution. Okay, so that, and so how do we detect this? So first, how do we detect this this potential here? We just put an electrode on and just measure what the voltage is relative to some reference point. It could be like sometimes they use the ears or the neck, or and if you've got an animal, you could just put an electrode into the skull or something like that to use as a reference point, and then you measure what the voltage is between that reference point and wherever you are. So that's the EEG data. What about the MEG data? The MEG data is a vector. But typically, and you record this with a SQUID, superconducting quantum interference device, which is this thing sort of like cooled down to, it's got little coils around little plastic thingies cooled down to liquid helium temperature, and you can record these very weak magnetic fields. But usually what happens is you typically record one component of B. So you might have if here's the head, you might just record the component of B in this direction. And so the actual B might be, say, in this direction. Sorry. So the actual B might be in that direction. But what you're going to do is you'll just record this component of B, like that's parallel to the head or perpendicular to the head. So, and you can put more than one detector in an MEG machine, so it can detect what is the component in this direction of the magnetic field, of the total magnetic field. So this guy is, the total B that we're detecting, and this is, measure one component, measure, one component in one direction. But you could put another detector in that would measure a component perpendicular to that, and then also measures a component, that's perpendicular to both of those. So potentially you've got more information in the MEG case, because you've got a whole vector versus just a number, but in practice, most of the detectors just are measuring numbers anyway. They're just measuring the component of the B field in a particular direction. So, okay, so before we talk about like sort of a more practical a practical forward solution, any questions about sort of the basic thing? So basically, it's just like a pair of charges, and a pair of charges defines an E field, electric field, and the electric field defines, after multiplying by the by the conductivity, it defines what direction is the current going to flow. And so what is that direction? Well, it's going to flow, notice it's the opposite of this. It's going to flow basically this direction. It's going to flow from the source down to the sink. And it's also going to flow, in various directions as you get further away. And if you then make the assumption that you're like 3 or 4 times the distance away, then you end up, instead of this very complicated mess here, when you get close to the dipole, you just end up with this simple inverse square law. So, and because of the cross product versus the dot product, you end up, these things are kind of perpendicular, the current. So this is, dot. This guy's cross. So you end up with these two parallel sort of forward solutions, both inverse square. So any questions so far? Okay, so now what would we do if we wanted to have like a more non-infinite brain head? Should be sort of a more useful kind of forward solution. So there's several different ways of doing this, and there's one analytic way of doing it where we can actually just directly write out an equation in one special case, and for the forward solution, because this just described like, so you have just one dipole in an infinite brane, and we could write out this equation. So there's ways of writing out the equation for a non-infinite head if you've got a spherical head. So basically, So in the case of, if we just assume that we've got a spherical brane, the brane is actually reasonably spherical. And we've got a spherical skull and a spherical skin. I drew them too thick here so I could write the labels in. So this is the brain, skull, and skin. So why do we have to include the skin? The skin is actually very important to include for the EEG solution, because the currents are actually coming through the skin. And in fact, a little bump in the skin right under the recording electrode is actually distorts the forward solution more than a thinning of the skull, because the recording, all the currents that you're recording, the voltages of those currents you're recording are coming right through that piece of skin. But let's just assume that the skin is exactly the same thickness, and it's a spherical head, and so you can actually have an analytic forward solution. Just write out an equation that will basically allow you to take a dipole from any position and calculate for each point on here what the forward solution is. Forward solution is just a number, just a weight that just says for a given amount of stuff in this dipole, how much, potential do you get here, or how much magnetic field do you get here? In the case of the magnetic field, the magnetic forward solution, we don't have to worry about the currents going through the skull and the skin because they're so small, and so we can just deal with, it's a simpler forward solution because we just say, like, where do the currents go in the brain? Those are the ones that generate the magnetic field, and the ones that came through the skull are so small we can ignore them. But for the electric forward solution, we have to pay attention to the skin. Okay, so that's, a lot of people use that. It's not too bad. A lot of people's heads are pretty spherical. So, but if you want to make a better one, you can do one called a boundary element method. And that one works by essentially making a something that sort of looks like a brain. There we got a brain. And just making, a triangular mesh of that brain surface, and then making a triangular mesh of the skull surface, and then making a triangular mesh of the skin surface. People often just kind of like cut it off at the neck. So here's the nose right there, okay? And so the way this one works is, so you end up having a whole series of mesh points here, and what you do is you just end up with a big matrix of correction factors. Correction factors to the basic inverse square forward solution. And so it will, the matrix will involve all of the different boundary elements. And the assumption here is that the conductivity and the permeability of the stuff that's inside one of those compartments is constant. So this is, constant, permeability, conductivity inside each compartment. And we know that's not true. And so it's possible to do a more complicated one, called a finite element model. The problem with that is that where do you get the numbers to put in there? So a finite element one, what you would do is, here's your brain and skull. You would just divide the whole thing up into just a whole bunch of tiny cubes. And then allow each tiny cube to have a different, permeability and conductivity. The problem with that is, where do you get those numbers from? So, you might think that would be the right thing to do, because that actually would directly be able to model, like, the skull. There's sutures in the skull where the different bones of the skulls come together, and current can get through those sutures a little easier. And then, you've got very thin bone behind the eyes, where the eyes, here's where the eyes are, his nose. That bone is much thinner behind the eyes than it is, up near the top of the skull. So for some of those things you have some data, but for a lot of them you don't. And so the end result is that you're potentially introducing all these different biases, because you don't have any direct way of trying to measure the different properties of each of those voxels. So so a lot of people use boundary element. There's a lot of software out there for doing this kind of method. So you would just take a scan, reconstruct the skin, skull, and brain outer surfaces, feed that in, and then you would get all those correction numbers to add on to our basic forward solution. But what's the best part of the basic forward solution with fixed dipoles? And so forward solution with fixed dipoles is linear. And so what does that mean? So first, what does it mean to not have a fixed dipole? So obviously your brain dipole is not going to move around. They're kind of where they are. But one way of trying to figure out the inverse problem, to figure out where the sources are given a bunch of data, is to take like a dipole, like a single dipole, and allow it to rotate around to try to minimize the error with the data you observed. So you put a dipole and allow it to sort of move up and down and rotate until it sort of generates a forward solution that looks like your data. That turns out to be a nonlinear optimization problem because you've got like cosines and sines when you start rotating the dipole around. But if you just assume that we've basically got a fixed set of dipoles, then we've got a linear problem. And so, what is a fixed set of dipoles? It's basically what, free surfer was, originally developed for. You've got some cortex here, and then what you do is you divide that cortex up into a bunch of little chunks, and you just put a dipole at each chunk perpendicular to the cortex, because, from current source density we know. So here's a unit dipole at each point. So if there's any current, it's going to be, it could be a negative number, in which case, the end result after multiplying by a signed solution, it could make it negative. But basically these are all the fixed, so these are, fixed unit dipoles. And so if you do that, the only problem is you need a lot of them, like about 10,000. So we'll see that's going to be a problem. But because we've only got about a couple hundred recording sites, we've got 100 or 200 recording sites, and we've got 10,000 things to solve for. So that's going to be a problem. We'll sort of see how to deal with that. But if we keep them fixed and just solve for their, so fixed unit dipoles, and then just solve for their amplitude, solve for amplitude, then we've got a linear problem. And what that means is, if it simplifies our life considerably. So what that means is, if we calculate the forward solution for a given dipole, so we've only got to do it once. So here's all the recording sites, and so each one of these forward solution things is just a number. It's just a weight that says, like, for that dipole, for a unit dipole at that position and orientation, how much of it do we see either electrically or magnetically at that recording site? So we basically just do that, and then let's do it for another dipole. So, what is that going to look like? What is the forward solution of that guy going to look like? It's going to look, something like that. If it was an electrical dipole, the electric forward solution is going to look like that. And so then let's just calculate the forward solution just once for another dipole. So here's another dipole. Make that one a little closer to the surface. So here's another one. And so now we just got to calculate that guy just one time, which is like, how much does it get to all those sensors? And what's that going to give? What's that forward solution going to look like? Well, it'll look something like that. And so the fact that the forward solution is linear means that if we turn on both of those at the same time, then we can predict what the forward solution is going to be just by adding those two forward solutions together. So basically we'll just get sort of the sum of those two. So this is forward. So that's forward 1. This is that in green. And forward 2 is just going to be equal to forward 1, forward 2. This is just, forward 1 plus forward 2. So that simplifies our life. We only have to calculate the forward solution once for each dipole sensor pair, and then it's fixed for all time. So, so what is the what's the bottom line is that this part is easy. Once we've simplified our problem to a linear problem by using these fixed dipoles that are perpendicular to the cortex, that makes our life easier. We just have to calculate the forward solution once. The downside is, to do this, we've got to, reasonably cover the cortex with dipoles, and that's like about 10,000, and so that turns out to be a problem. Okay, so any questions about this? So this is just the forward solution. So this is just predicting for some current in some place. What are we going to get at our sensors, either electric or magnetic or both? Yeah.
In the physical world, how do you place a dipole? What is it physically?
What are you placing here? Well, you would typically, to sort of set up these set of fixed dipoles, you would reconstruct the cortical surface, like the peel surface, and then go, say, halfway in between the peel and the gray-white matter surface, and just say, at that XYZ point, there's a unit dipole pointing in that direction. So it's going to be perpendicular to whatever that cortical surface is. So if the cortical surface is, say, coming out like up at you this way, then the dipole is going to be perpendicular to that surface at each point. Okay, over at the Learning Glass, time to quit before we go over the forbidden zone.